Here we will see components of microservice architectures. A microservices architecture structures an application as a collection of loosely coupled, independently deployable services which are organized around specific business domains. It maximizes scalability, fault isolation, and development speed, though it introduces complexity in distributed data management and inter-service communication. Different components of microservice architectures are API gateway, microservices, database, server communication, authentication, logging and monitoring. First is API gateway. An API gateway acts as a single entry point for all client requests in a microservices architecture. It sits directly between external clients and internal microservices, which handles cross-cutting concerns. So your individual services can focus purely on business logic. Without an API gateway, client application would have to talk directly to dozens of independent microservices, which requires complex client-side routing, multiple authentication points, and high network chatter. Then microservices. In an ASP.NET Core microservices architecture, a large application is broken down into small independently deployable services that communicate via lightweight protocols and manage their own isolated data storage. When building microservices with ASP.NET Core, several architectural patterns are commonly implemented to ensure scaling, isolation, and resiliency. Microservices must interact with each other to complete complex business processes with synchronous communication and asynchronous communication. Then database. The foundation role of microservices architecture is decentralized data management. That is, each microservice should own its data and database. It shares a single centralized database across different microservices, which is a major anti-pattern because it creates tight coupling, breaks service independence, and causes single point of failure. Here, services never query each other's database directly. They communicate strictly through APIs or events. For example, order service, product service, payment service, etc. Then service communication. Microservices require structured protocols to talk one another securely and efficiently. These are generally balanced with synchronous and asynchronous paths. Synchronous path is used when a real-time response is required, which is implemented via standard HTTP client calls or high-performance gRPC protocols. And asynchronous path is used to decouple services during transactional updates. One service publishes an event and interested services consume it. This is often automated using packages like mass transit over message brokers like RabbitMQ or Azure Service Bus. Then authentication. Authentication in microservices verifies the identity of users and services across a distributed architecture. It depends on decoupled stateless approach using centralized identity providers and token-based mechanisms like JSON Web Tokens rather than traditional server-side sessions. Securing a distributed system involves two primary traffic flows. First, user to service. Here, external clients rarely communicate with individual microservices directly. Instead, all traffic flows through an API gateway, which centralizes the heavy lifting of security. And service to service. Once a request is inside the perimeter, microservices often need to communicate with one another, which leaves these internal communications unverified, which poses major security risk. Then logging. Logging is the process of recording information about the execution of an application, such as user requests, errors, warnings, and important events. In microservices architecture, logging helps developers to monitor, debug, and troubleshoot applications that consist of many independent services. Unlike monolithic application, a microservices application has many independent services. When a request passes through several services, it becomes difficult to determine where an error occurred. Logging helps to track requests across services, detect errors and exceptions, monitor application health, analyze performance, debug production issues, and audit user activities. And monitoring. Monitoring microservices requires tracking distributed independent services by correlating three telemetry signals: metrics, logs, and traces, often called MELT. Metric is a numerical representation of system behavior. They are ideal for dashboards, alerts, and tracking system health. Logs are textual records of events which are happening within a service instance. It uses centralized log aggregation to search across all services easily. In distributed system, logs must include a unique trace ID to correlate events across different services. And traces. It is the most critical tool for microservices. Traces follow single request as it travels across multiple service boundaries, which allows users to see exactly where latency builds up. This approach ensures that you can pinpoint which specific service or network dependency is causing bottlenecks or cascading failures.